Hello, hello, hello. Welcome to Twitch Stream Thursdays. I am Mofi and I, of course, have
Nick.
here with me. So, Nick, today we are learning more AI stuff. Tell us,
Yes.
what are we learning?
So today we're going to learn some more layer types. And sadly, we aren't going to be doing any coding today.
Or math.
Or math.
I'm sad.
Well, actually, there is a little bit of math.
God.
But it's like arithmetic.
Okay. I can deal with
But,
arithmetic. Okay.
Yeah, so I have a nice presentation. It's going to be a nice PowerPoint day, no code.
Hey, keynote.
We're going to be, keynote. We're going to try and keep it under 30 minutes.
30 minutes. Okay,
We can do this.
That's a bold promise.
Let's try to get 15 minutes stream today.
Okay, that's a bold promise from Mr. 1 hour 30 minute.
Yeah.
Okay, all right, but let's jump into
That's
it.
why I'm saying 15 minutes, because then maybe I'll actually go a half hour.
Okay, cool. So I'm gonna just jump you on play and take it away.
Awesome. All right, so we have some rectangles inside this little image here, right?
You do, yeah.
So our goal, we want to try and understand what's happening in this image, right? So we see two squares overlapping each other.
Uh-huh.
And previously, when we were talking about like MNIST and our numbers, and if we draw the number like in the center of the screen, it'll work okay. If it's anywhere outside of the region of comfort of where all of the letters were when we were training, it's not going to do so hot.
Right.
So we kind of need a way to reuse knowledge throughout. So actually, let's connect this iPad first.
Okay.
I want to do some drawing.
I mean,
Going off script.
I mean, it's only been 30 seconds. Of course, you would go off script. Okay.
Beautiful. Where we go?
We went.
You probably quit on us.
Probably did. All right, do it again. It was tired of your shit. It was like, no more.
Right.
Okay, I'm gonna just also move it just a little bit to the left so that we don't block. What did you do? This time?
Just opened up notes. Oh man,
It just
what happened?
to no idea. Hold on. Forced landscape left, but it's seeing more of the screen than it should.
It's fine. We don't care.
Is it? Okay.
All right. Yeah. Cool. All right. So, wow, that's really awkward.
Right?
So let's. Here's our nice image, right? And we have like this super cool blue smiley face inside this image, right?
Mm-hmm.
And let's say we train a neural network to learn this face,
Okay.
this smiley face. It knows exactly what this smiley face looks like. But then if we have another image, let's say it has two smiley faces. It has no idea that these two smiley faces are smiley faces because they're completely outside the scope of our original smiley face. However,
Size-wise.
yeah, size and position
yeah.
and a lot of factors. What if we could take the information that we learned in this first one and kind of apply it to smaller parts of this image? So like say we take this, is this app different side? Maybe. Okay, so say we take the information we learned here and we kind of shrink it down and apply it to here, and then we kind of just like keep applying it throughout the image so we could reuse this information. So we don't have to train it that a smiley face could be in this top left corner and the top right corner. We just need to teach it what a smiley face looks like, and it'll kind of search the image a little bit.
So is it doing it for like any particular scale or all scale? Like for example, if you had like one smiley face this big, one even smaller, like how, you know?
Right, then we would kind of have to start training it for smaller and smaller. And that's kind of where I'm going to. When we're doing image recognition, we don't take this entire concept of a smiley face and sort of look over the entire image. What we do is we break the smiley face down into smaller parts.
Okay.
So we say we want to like look for like this small sort of curve. So we look all over the image for this curve, like we see one here, and if we look here, we'll see it here and here. And it doesn't really matter as much how small. There's a little bit more of wiggle room just because that curve kind of looks similar no matter how big it is.
Right.
And same thing with like a vertical line. It doesn't really matter how tall or big the vertical line is. It's going to look like a line kind of.
So what we were basically saying that we're trying to look for feature rather than just the whole thing at a whole, like at the beginning. Okay.
So we're going to start looking for these smaller features and sort of build on them and use those previous features in the next layer to kind of figure that out. And I think now let's go back to the presentation.
Okay. Sure. How do I I'll just quit this. This was okay. Let's head back.
All right. So we have these two squares, and let's think about what we were talking about with the faces, where we want to break it down into smaller features.
So our goal is to detect squares in a picture.
Yeah, that's what our goal right here is, to detect squares. What's kind of like the first feature that sort of stands out at you, like that we could try and find?
For a square, I think lines, vertical and horizontal lines.
Yeah, perfect. So how, looking at this image, like what's one way that we can kind of find vertical lines?
I mean, I would basically just like, if I think of an image, right, I'm thinking like a 2D matrix, and I'm just gonna say like the point where it goes from white to a darker color, that's probably where I have a line, and I can just like look for those points.
Right. Yeah. So there we go. So if we look at each of these various points on the image, and we compare the difference between the points on each side of like this midpoint, we can kind of start to tell how big like depending on how big the difference is, there's probably a better chance that there's like a pretty sharp line or edge in that point. So like if you look here, 255, 114, that's like a pretty big difference. 114, 153, it's not as big of a difference, but it's still a difference. And then here in the middle of the square, 153, 153, there's no difference at all. So we can kind of rule that out. And same thing with the white space. So how can we sort of translate this to some kind of math that we can apply to our image? And
I think the selector is there. There you go.
So now we're going to go back to the iPad.
Boy, I just got to the iPad. Okay,
I'm so sorry.
It's okay. I thought you were changing the script, like just moving things around, but it turns out you were
just going all out somewhere else.
Hopefully this time around actually will get better, because 2588. Yeah. I have no idea why this is happening.
What happens if you try and can you shrink this at all?
I don't know. Hold on. I'm gonna try this. What if I give it?
I feel like it thinks it's in like landscape or portrait mode. I feel like
it shouldn't though. Okay, hold on. Because I see that it did change.
That's not
automatic orientation. I'll give it, and I'll give it default size. It's just like completely disregarding every single thing. Well,
it doesn't matter.
It's okay. It's cool. Full screen. Okay, I gotta change something, but anyway.
Okay.
Probably add another page so that doesn't. Okay.
Cool. All right. So when we were looking at our line, we had like this point here in the center, and we had a point on either side, and like one was colored and the other wasn't. So when we're looking at our image, I think last week we kind of talked about how we take the pixels as they are. So like 0 would be either white or black, depending on how you're dealing with it, and same with black or white, back and forth. One of the other.
Okay.
So let's say in this scenario, white is 0, and let's pretend this blue is black, and so that's 255.
Okay.
So let's say we're looking at this little sort of window right here.
Right.
Where we have like this left value, this middle value, and this right value. What if we wanted to turn this into math? So let's call this like just do question mark times. So this is 0 plus question mark times this. I guess let's pretend this one is blue. So times 255 plus question mark times
again 255 because that's in blue, right?
255. And our goal, we want the difference between these 2 points, right? So we would want it to be 255. Oops. So what could we replace these question marks with so that we can end up with this 255?
I mean, there is probably infinite number of solutions, but I think in this kind of like a moving window kind of a thing, we're probably looking for like 0, 1, 0. So we find the line in the middle. Is that what we're doing, or?
So.
I mean, 0, 1, 0 will solve this problem. That's what I'm trying to say.
0, 1, 0 would solve this problem, but we're essentially we would just be picking this point then. And that point could be anything. That could also be 0.
Yeah, we could probably do...
And then that would be 0. Because we're trying to essentially compare these 2 points, right?
Right.
And before we take the difference between them. So like 255 minus 0 is 255.
Right, so we'll probably do negative 1, 0, 1. That...
Yeah, so if we did negative 1 times 0 plus... What would this one be?
We could do that for 0 because that's the center point.
Times 255 plus, and then what did you say here? 1.
We're basically saying I want to subtract that value from this, like this value from that value, right?
Right. So then, yeah, we would end up with 255 minus 0, and that would give us exactly what we want, 255. And then, so we can kind of turn this into like a little matrix for our weights.
Right.
And then these are kind of like exactly like our fully connected layers that we were doing before, where each one of these is multiplied by a number, and it gives us, oh, geez.
Sorry, got a call. I don't know who would call me this time, but
we can kind of think of like, it's similar to our fully connected layers where we're multiplying each one of these by some value and adding them all up together to give us a single value. So we would apply this, these sets of weights to our pixel data, which was like 0, 255, 255, and then we end up with a single output of 255.
Mm-hmm.
And we want to pass this this matrix all over the image.
Okay.
Just kind of slide it over and calculate that for each portion of the image. And then we'll kind of end up with a map with all of these values.
Right. We get like a new kind of image.
Right. With these values highlighted. And then I think we can go back to the presentation.
Do you need the iPad?
I don't think we need the iPad.
Okay.
Anymore.
Cool. Well,
no promises, though.
I'll take it. Well, that didn't work, but I'll do this. There we go. And voila.
All right. So here's what we have. So in here, we kind of expanded this to 3 by 3, just because when we're doing convolutions in an actual system, there's square matrices. And as you can see, it's passing over this little corner, and it's calculating out like this sort of like almost a new image where the edge is a bright color and the rest are dark.
Right.
Makes sense?
So basically, the point it did find was, I don't know if my mouse is being visible here, but it's going to be just like this line right here, right?
Right.
That's where the difference is.
Right, and so you can kind of see how like the image is slightly smaller than the
because
previous.
of the buffer of the so that it doesn't overflow, right?
Right, okay. And there's when you're doing convolutional stuff, you can kind of choose your own padding. So sometimes people will pad the image with 0 and pass the convolution over, so you end up with the same size image as the output. But here we're just kind of bound by.
Right, you're just being lazy. That's what it is.
No, it's preferences.
Well, you're losing information on the image, so I don't know. Anyway.
So yeah, that's what it's doing. It's finding us edges. And so if we pass the same convolution over this image that we saw previously, we would kind of expect to get something back like this, where the edges, at least the really bold edges, are highlighted. And you might notice we're missing some of these edges, right?
Yeah, because like the current one we have only gives us like this line.
Right.
Yeah.
So what we do is we need to do convolutions multiple times, and we're going to have all different kinds of angles, different sort of sub sort of features that we're trying to find. And we're not the ones that are coming up with these weights. Just like with our fully connected neural network, it's the process of training is how it sort of finds these values. So in reality, a lot of times our these sliding windows that we pass over the image, we call them either filters or kernels.
Okay.
But yeah, so those are our weights, are these filters and kernels that we pass over. And that's what the computer kind of starts to figure out, like the more you train it. So here's a pretty simple convolutional neural network. This is taken straight from the Keras documentation as an example of training a convolutional neural network on the MNIST dataset like we saw previously, except this time it's actually using the convolutions. And I'm going to go through kind of layer by layer to show you like what each one of these things are. Because right here we have conv2D, max pooling, dropout, flattened, dense, dropout.
All sorts of things.
A lot of new things that we haven't seen before. So to start, this conv2D, that's just convolutional neural network kind of layer, what we just were going over. And the kernel size is 3 by 3.
So we're doing a 3 by 3 convolution, those window, okay.
And again, we still have these activation functions. ReLU is what we're using in this case. And we know how to do that, right?
Yeah. Well, hold on. What was ReLU again?
ReLU is the activation function.
Right,
so
right.
That's
like
the function we apply.
I know,
but it's the one that's kind of max 0 value.
Right. So it's like this.
Right.
Yeah. Okay.
So anything below 0 is 0. Everything above
it's just X, whatever the value is. Yeah. So I just remember ReLU as like this.
Right.
Okay.
Yeah. So starting with this convolutional layer, we have 32 convolutions. That means we have 32 different filters
and we didn't decide these filters.
Right. It's whatever makes it the most sense for it to learn.
So throughout the steps, would it keep changing this?
Yeah, so each training iteration, they'll like slightly change, just like how the weights in the model change.
So, okay. One another question. So in the weights on the model, right, we change the weights because we want the difference or the error to go lower and lower.
Right.
What is the...
Same thing.
What is the error then?
We still want the error to go down.
But like...
because that's the output of the function. This convolution is just one portion of this
function.
That's
what I was
saying. It's just kind of adding... it's essentially the same thing as the dense layers. We calculate the error the same way. We just need to find the derivative of these convolutions. If that makes sense. Does that make sense? So how we're changing these weights, how that affects our error function.
Right, but never mind. Go on. I'll have a question later.
Okay. So yeah, we have 32 of these filters, and that's just a bunch of weights. So 32 filters, and we have a 3 by 3 kernel size. So that's essentially 3 times 3 times 32. That's how many weights we're trying to learn.
Right.
And yeah, so this is what one of these 32 kernels might look like. It's the same like 1, 0, -1 sort of thing that we saw earlier. And then so here's an example of after passing 32 convolutional passes over this image with the different kernels. Here's our 32 different outputs. So we end up with like 32 sub-images, and this is an actual output. This is just something that I made up. Most of them are just completely black. It didn't pick up anything. Some of them kind of like picked up the edges on the 4. Make sense?
So each of the squares are a representation of this number 4.
Right.
After running the convolution, like that window.
Right.
Okay.
So we end up with these 32 separate little layers. And then we have a second convolutional layer that we're doing. And it's pretty much exactly like the previous one, except now that it's the second, and we have to take into account all of the previous outputs. And so, like, how would you think you would handle that? Would you do convolutions individually over like each of the separate output? Like, so how would you run the convolutions over like this? If we had to do 64 new convolutions, what would you do?
I'll probably just get rid of the ones that doesn't have anything first, and then the ones that have something, I'll just run the same convolution over.
Okay, so like you would end up doing like 64 passes over like each one of these.
Or probably there's a way to like flatten this into like one image again. If I put all of them on top of each other again, I don't know.
Right. Yeah. So that's one of the things that I was kind of like unsure about whenever I was first learning this. I didn't really know if it was running over all of these individually or if it was like somehow like stacking them together.
Mm-hmm.
And what it does is it does stack them all on top of each other.
Okay.
And the reason why we do that is because it won't really be able to learn anything new from like the previous shapes. So if you think about an image where you have like a horizontal line and a vertical line.
Like our square image.
Like our square. When they're on separate images and you're running them independently of one another, we can't really get any more information off of like this straight line and this other straight line independently. But if we kind of stack them together and we see like, oh, there's horizontal lines on this layer and above there's vertical lines, we can kind of like use the information together to kind of like as a building block to like put more complex shapes together. Does that make sense?
Yeah, no. That's exactly what I was going to say.
Good.
Okay.
Good intuition. So now we have 64 convolutions. Our kernel size is still 3 by 3. Here's an example.
So could you go back once before you look at fancy animation? So like this number from 32 going to 64, is that more of a like observed like intuition, or is it like a thing you need to do always double it?
It's just something that works.
Okay.
It's something
like
you play around with.
For example, what is stopping me from going to the 128 here?
You could do that too. It's just you also don't have to use 3 by 3 kernel size. You could use something much bigger.
So from the next from layer 1 to layer, so not layer 1, like step 1 to step 2, I could even change my kernel size then.
Yeah.
How about changing activation?
Yep. Yeah, you can do there's tons of little tiny hyperparameters that you can change.
Right, but
that's something you just kind of have to play around with, get some intuition. I feel like a lot of people, they at least use multiple of 2s when they're like kind of picking how many things.
Okay.
It's the same with when we were choosing our dense layers.
Right.
We could really use any numbers we want.
I mean, but like at some point, like using the number has some benefit over not. like speed versus more accuracy versus more.
Right.
So
yeah, the more convolutions you have, like obviously the slower and like larger your model will be. And it's just kind of a matter of if we had 32 in the second layer, and we try it also with 64, what's the trade-off on speed and what our final accuracy is?
Right.
And if we did drop this down to 32, it would probably give us about the same.
Okay.
It's hard to say, but it's just something that you kind of tinker with, and I feel like what I've seen, I think people kind of like this sort of like idea of symmetry and kind of like increasing and decreasing, which it might not have any effect on like how well the model will do, but I normally see like in dense layers, like it starts out small and it kind of like evenly grows up big and then like evenly shrinks down to something small, where you might.
It probably would be just like fun to mess with it. Just do like odd prime numbers for layers. Just go from like 31 to like, I don't know what the next prime number is, like 51.
Right.
Oh, 51 is not a prime number. Damn it. 57. So go to 31, then go to 57.
Yeah. Yeah. I mean, it's something to try. It's one of those things you just kind of play around with, and then you kind of notice things that have a big effect and that don't really matter.
Mm-hmm. Okay.
So here's our nice fancy animation. We stacked up all of these outputs on top of each other, and now we have kind of like this 3D convolution. But this is still technically called a 2D convolution because it's only moving in 2D space.
Yeah, because also I think because all these layers that we have from top to bottom,
right.
When you're doing the math, you're basically looking at them as one layer because all of them are stacked on top of each other. Kind of. So each node is multiplied by the value in the thing, and they're all added up together. So we don't really flatten the values per se. But like we look at it at the same time.
Right.
We're
looking at like that giant chunk, all this.
Like all the whole column, each column. Okay.
Right, and then so this is like passing through. This one, I'm not sure how wide this is. This looks like 8 or 9 or something.
I mean, convolution usually is an odd number. Like
right.
Usually it's 9.
Yeah. So in our example, that would only really be 3, but
right.
This one was a much bigger kernel. And then so we do this 64 times, 1 for each of our 64 kernels, and we end up with 64 of these outputs.
I mean, now I put it closer to you. You don't have to go.
Okay. So now we have this max pooling 2D. And it's kind of like convolutions, but not. And this pool size is pretty much just the same thing as our kernel size.
That's it. I just said we use convolution for odd numbers. Now you show me. Damn it.
Yeah, max pooling people normally do 2 by 2.
Okay. So what is max pooling?
Anything different. So yeah, I'm going to go over max pooling. So this is what max pooling is. It's essentially still a convolution, kind of. You're moving this box over the image, and then inside the box, like the convolutional filter area, we're picking out the max value.
Almost like sampling, but like just like.
Yeah, exactly. That's pretty much what it is. So when our what's it called? Our pool size is 2 by 2, and that means our kernel size is 2 by 2, and it moves 2 pixels at a time. So whereas our convolution, it was only taking a stride of 1.
So basically, essentially, whatever 2D array it had, just drop the size to 1/4.
Exactly.
Okay.
Yeah. So you pretty much take the output, you split it up into 2 by 2 chunks, like a nice little grid, and you pick the highest value.
So is it for like speed reasons? You made it smaller, it's easier to calculate other stuff?
Yeah, that's exactly what we're doing. We're just shrinking it, essentially.
But like, could there be cases where max pooling would lose so much data that like essentially you're dropping 3 of the 4 pixels
on
an image?
So we're throwing away a ton of data, and it can be an issue. And there's a lot of papers out there that kind of go over like why like different approaches to max pooling, so that we can still kind of shrink down but keep better information. Because here we're kind of just sort of throwing away like stuff at random. We're just kind of paying attention to the noisiest of them.
Yeah, like for example, in this particular case, right? Like for example, you have like 9, 5, 4, 1, right? Like 9 is definitely the most prominent out of the 4 pixels around it.
Right.
But in an image, if it's like a very like colors and the shapes are very close to each other. Like for example, if you had 9, 8, 8, 7, and if you just take the 9, the 8, 8, 7 might be also important stuff.
Right. And there's also something called average pooling, where it just takes the average of that square.
Okay.
But I think max pooling seems to be the most common that I've seen. And it kind of makes sense intuitively, just because if we think back to our original like convolution that we did with the square, the value with the sharpest edge, that was our loudest value. So we're kind of ignoring the less defined lines and focusing more on like the really sharp edges.
So basically, because it's the most sharp, highest value, because everything else is no difference between if the same color. Okay.
So we're kind of trying to cherry pick the important information. And then, so you were exactly right. Why do we do max pooling? When we had, before max pooling, we had 64 output layers, and each one had 28 by 28 nodes. That's not exactly true because of...
we dropped
a couple, so it would actually be 24 by 24 nodes. And that ends up being like 50,000 nodes, which, putting that into our dense layers at the end, that's like a lot. We're max pooling, we can drop that down drastically down to like 12,000 nodes. But yeah, a lot nicer to put through our neural network. And then we have this new thing, Dropout. And what that does is it's randomly shutting off nodes. So 25% of the nodes were like, you can't use this road right now, kind of thing.
On each step or overall entirely?
So each training step, we turn off 25% of the nodes, and that kind of forces us to find a new path. And that can help us prevent overfitting. Okay. So it doesn't like...
So is the also the 25%, is that also like kind of like play around with it, what number works best?
Yeah. Yeah, pretty much anything that we're specifying here are all things that you play around with. Otherwise, it wouldn't give us that as an option. You know?
Okay.
And then we're going to do a flatten, which I think we talked about a little bit before, but I made a nice little animation. So here's a bunch of our outputs. It just makes one little line those are our input nodes into our dense layer. And our dense layer had 128 nodes. And then we have another dropout. So we're turning off 50%. And finally, we have our last dense layer, and that is just our output layer. So we would have our 10 for each number.
Okay, so what are the softmax again?
Softmax was the one that we used for classification.
No, I'm thinking of the graph.
Graph-wise, I don't know if there's like a good graph for it. It's the one that kind of compares, it pretends each class should be 0 except for the one that you care about. Remember? It was like the log of the like predicted.
Oh yeah. No, I remember now. Yeah, it didn't have a good graph.
Right.
Because most of the ones I remember by what the graph looks like.
I think sigmoid is probably the one you're
thinking. Yeah. I remember most of them by that graph. So
yeah,
I need to do actual studying under this.
Yeah, that's pretty much our network right there.
Okay.
Makes sense. Is there anything you want me to go over more?
Maybe this one again, the dense 128, where the 128 came in from.
So that's just, again,
just a number, just like you're throwing numbers out.
That's what
and I saw a couple of examples as well. Most people kind of also go. I mean, I see that the power of two is like a big player in this game. Yeah. Is it?
I don't know if there's any reason for it aside of the fact that like engineers like.
When I initially first saw it, I thought like using power of 2 makes it easier for probably the library to do it because power of 2 are easier to calculate. Possibly. You can do some little bit of more optimization in terms of multiplying and dividing power of 2. Instead of actual multiplying, you can just do shifting. But looking how long Keras takes to get started, I don't think they're doing bit shifting.
And I think the only thing that I have seen that makes sense is the kernel sizes are normally odd, and that's just because...
I mean, center. Otherwise, kernel won't have a center.
Right.
You will have to do an average of the thing anyway.
Yeah.
So...
Yeah.
But I think we made good time. We made really good time, Nick. Anything? Hold on, let me just get back to our faces because... There we go. So, Nick.
Yeah.
From where do we go from here?
Where do we go from here? We will do code next time.
Excellent. So will I be doing code or will you be doing code?
Maybe I'll make you do some code.
Okay. No, I'm gonna.
We're pretty much just gonna implement what we talked about here.
Right. Okay. I'll just memorize this.
We're not gonna write it from scratch. We're just gonna use Keras, and then we'll try to demo it in the Node React kind of drawing app.
So. Couple of other information next week. So we could next week is
all right. It's gonna be we're
next
going
week,
all
next week is like a kind of a curveball for everyone. So
next week I'll be with Pooja and we'll be doing.
You might be right.
Okay.
So next week I'll be in DevOps Portland. So if you're there, please come say hello. But next week I'll be there. So I'll be with JJ, who is also a developer advocate and does a lot of cool Kubernetes stuff. So if we have the time and the resources to do it, we might do a stream on Kubernetes next week. Or, also cool stuff, Pooja does a lot of Node-RED, so she might also be showing that off next week. So we still haven't figured that out completely, but it'll be out on Meetup page already, or we'll tweet it out.
Yeah, so you'll be gone 2 weeks though. So I think what me and Pooja were going to do is next week on Wednesday, we were going to do
so we actually can do Wednesday and Thursday next week.
Yeah.
Let's do it.
Okay.
Let's do it. So Wednesday we have a stream. We're doing basic of Node-RED. Thursday
we're gonna do telodrones, and we're gonna show how to stream and fly with Node-RED. And then the next week, we're going to add in object detection into that.
Right. And so next Wednesday, we have that. And next Thursday, hopefully, we'll get to see a live conference a little bit of a live streaming from a conference. And then Thursday after that, Nick and Pooja will also again join in.
So we'll add the object detection.
Do a little bit of
drones.
Yeah, on a drone. And we actually gave out a bunch of these drones a couple of months ago. If you were one of the lucky winners, congratulations. If you didn't, hopefully we'll do something similar soon again. And the week after that, I'll be back and we'll figure out what we do.
And you'll do Kubernetes and I'll do, we'll go back to normal.
We'll get back to normal. So with all that, thank you again for joining. And hopefully this video will be up as soon as Nick uploads the video. Right?
Yeah. A couple weeks probably.
It'll be up on YouTube soon. And thanks for joining once again. And take care.